Hello and welcome to the world of NDE 4.0. My name is Johannes Reiner and today is a great day because today we are coming back to the world of ultrasonics. Now last time we started with the early history of ultrasonics, and within those videos about ultrasonic testing I will actually guide you to the world of NDE 4.0. This will become one of the showcases of NDE 4.0. But today, after we discussed the very basics, the very early start of ultrasonic testing, we are now getting into the basics of ultrasonic testing and ultrasonic sizing. So let's get started. Now, talking about ultrasonic testing, most of ultrasonic testing is the so-called pulse echo ultrasonic testing. And in pulse echo ultrasonic testing, what we have an instrument, and that instrument actually produces a high voltage electric pulse, a very short high voltage electric pulse, something like in the range of 250 nanoseconds, or even shorter. Now that high voltage pulse is brought onto our probe, and that probe actually creates a mechanical vibration. Now, that mechanical vibration of the probe is then brought into the component. And as you will know from your doctor, you need some coupling in between. You need some water, some coupling gel, some oil, or also could also be hand lotion what you put in between. Doesn't matter. What matters is that this liquid actually helps to bring our ultrasonic wave from our probe into our component. Now, once that very short pulse is finished, then the instrument switches from a sending to a receiving mode. And it's this very same probe which is actually used for sending, which is also used for receiving. So now, what happens is we get our acoustic wave exiting our probe, entering our component. Or to be exact, traveling back and forth between the probe and the surface of the component within the coupling medium. So during the first few 100 nanoseconds, actually what we will see is only the wave going back and forth, and that actually saturates our probe. So that's why in the beginning we have a so-called dead zone where we do not see anything. After that first interaction has died off, then actually we start to see some signal coming back from our material. And our wave starts traveling into the component. Here we see where our wave is at this moment of time. It's traveling further, traveling further. Now it's hitting our defect. But if we look onto our screen, and what we see on the screen is to the top we are seeing the amplitude, to the right we are seeing the time our sound needed to travel, or we can also calculate that into a sound path by applying the speed of sound. Now, if we look onto that so-called A scan, which we see on that instrument, why do we not see that indication right now? It's pretty simple, because that wave just traveled to the indication, but it also has to travel back from the indication back to the surface so that we can see it. All what we have seen up to the moment of the A scan is actually the dead zone in the beginning, and then some noise from the first half of our component. Now we are getting into a wave which is reflected back from our defect, but another one which is traveling further to the back wall. Okay, now we are hitting the back wall, and that wave gets reflected also on our back wall. So now we have two waves coming back, one from our indication and one from the back wall. Now our first wave actually hits our probe, and now we are seeing the signal on our A scan. And a couple of hundred nanoseconds later, we also see a signal from the back wall. So this is a typical screen you see on a pulse echo A scan. You can see something like that. That's typical signal of an indication. You see the dead zone and you see a back wall. Now, finding indication, that's one thing. The other side is sizing those indications. And if we have, like in this example, a pretty large indication in that component, and we have our probe on our component, we start our ultrasonic pulse, we're getting back our signal, and then we are making a dot where we found our indications. That's that dot. Then we move our probe, we fire again, we get another signal, and we mark another dot. And we do that a third time for a third position. So then we can say, okay, that indication has a length going from here to here. Now, this can be done not only in one direction, but also in the second direction. But it's only true for indications which are actually larger than our beam diameter. Because if they are smaller, like in this case, now the first reflection is about the same. But if we now move our probe, we can actually still see that very same indication. But because what we do with ultrasonics, we actually know the distance to an indication, but we do not know the angle. The only thing we know is the distance and our probe position. So if we want to mark now this reflection we are getting from this probe, we are marking it at the position of the probe, at the distance to the indication. So we are marking it here. And if we do that multiple times, then what we actually get is those crescent shape indications, which we find in a lot of cases. And here you can see a real one from a real inspection. So how do we size indications which are actually smaller than the beam diameter? Now, if we go one step ahead and say, okay, we have here this artificial probe or this artificial sample we have with our indication, and we say, okay, at a certain sound path, we are getting a certain amplitude as a reflection from our indication. Now we are grinding off the top half of it, making it shorter, making the sound path shorter. And we are getting a different signal. We are getting at a shorter sound path and with a higher amplitude. We do that over and over and over and over again, and we see that this actually follows a certain dependency. Now, if we make our indication bigger at the same sound path, then actually we shift our curve. So we have a correlation between our sound path, our amplitude, and our size. Now, one method to use this correlation is so-called distance amplitude calibration blocks, like you see them here in this set. And each one of those blocks has a flat bottom hole inside. So you put your probe on all those different lengths with all those different flat bottom hole diameters, and you get those curves. And once you find a real indication, then you compare the reflectivity to the reflectivity of those calibration blocks, and then you can say, okay, this indication actually reflects like a flat bottom hole with 1 millimeter diameter. Now, to get really decent numbers from those blocks, that's a lot of work. And if we think about big components like large forgings, we're getting in those sizes of calibration blocks. and they are not anymore really that handy. So people already from the very beginning of ultrasonics thought about, okay, how can we make our lives a little bit simpler? And there were some early books from around 1950, one from Kinsley and Frey, and they really worked on the first theoretical approach for a so-called distance amplitude correction. And the book from 1956 from Setti, Granato, and Truel, that is really more or less the basis for all those theory-based methods which followed later on. For example, that one from Ying and Baudry, which actually used a single flat bottom hole for all the calibration, and all the other stuff they did with a lot of math. There are also multiple methods using just a backwall signal and then using math to actually come up with the size of the indication you found. And those methods also have one benefit, because you can actually also give a sensitivity information. But we will come to that perhaps in a different video. Now, there is one method which is very common here in the European area, which is called the DGS method. And what the Kraut-Kramer brothers did back in those days, actually, they took all the existing theory they knew, then combined it with a lot of experiments they did, and they produced easy to use diagrams. Now, those diagrams, sometimes they look a little bit challenging in the beginning, but I think I will be doing a video about them, detailing a little bit how they work, because they are actually not that complicated. And it's a really good tool, number one, to actually get the sensitivity of your measurement, to know, okay, I will be able to detect indications above a certain size. And number two, it makes also, the measurement of indication sizes pretty easy, just by going onto this diagram. Now, whether or not you want to still use those diagrams in the digital era, that's a different story. But back in those days, that was a fabulous idea. Perhaps nowadays, the data which makes up those diagrams would be better off in a computer, helping you in a digital way. But that will be NDE 3.0 or 4.0. So we talked about the sizing for large indications, where we move our probe and then we can say, okay, it goes from here to here and from here to here, and that's our size. And we have another one where we put our probe on our indication, we get a reflection, we maximize that position to maximize the reflectivity, and then we compare the reflection to a reflection of an artificial reflector, like a flat bottom hole, a disc-shaped reflector, or a side drilled hole. And then we can say, okay, we can give a size information. Now, this is not the size of that indication. This is just an information about the size, an indication about the size. So thank you for watching this video. If you have any comments, if you have any questions, feel free, or please write them down here into the comment section. Next time, I guess I will be speaking about ultrasonic waveforms within here this ultrasonic segment of this channel. Within NDE 4.0, we will be speaking about data security, data safety, stuff like that. As usual, you will find more information down here in the description. I hope you liked this video. I hope you will subscribe to this channel. I hope you give me a thumbs up. I hope I will see you soon. So thank you for watching. See you soon. Thank you and bye.